Hi everyone, I am 𝐓𝐸 and this is our work, TFFM, Topology-Aware Feature Fusion Module via Latent Graph Reasoning for Retinal Vessel Segmentation. Here we introduce a new module called TFFM, designed to fix a persistent issue in this field, the problem of disconnected, fragmented vessels. We all know retinal segmentation is crucial for diagnosing diseases like diabetic retinopathy, but usually when we build our model for this, we focus heavily on pixel accuracy. We want to get that high chi-score. However, there's a catch. Clinicians do not look at images pixel by pixel. They look at the vascular network. They need continuous trees to track blood flow and extract biomarkers. This slide highlights the core challenge we are addressing. We all aim for high pixel accuracy and metrics like chi-score. They tell us how well we are capturing the vessel regions. However, the problem, to a clinician, a vessel is a continuous network. To a standard CNN, it's often just a collection of independent pixels. You might have a model achieving a stellar 95% chi-score, which is obviously good, but the output could still consist of 50 disconnected fragments. Our goal, therefore, was to bridge this gap, maintaining that high accuracy while ensuring the vessel actually connect. Our solution is twofold. First, we introduce Topology-Aware Feature Fusion Module, TFFM. Instead of just stacking more convolutions, we project the feature maps into a latent graph space using graph attention network. This allows the network to reason about global vascular structure, which standard convolution often struggle with. The second part of our solution is the loss function. We designed a hybrid loss combining Chebyshev loss and soft cell dice. The soft cell dice acts as a topological regulator. It penalizes the model if the predicted skeleton is broken, forcing the network to maintain continuity. Just to give you a quick overview of the result, we achieved a 90.97% chi-score on the fundus 𝐓𝐸 dataset. More importantly, we reduced the fragmentation about 38% compared to the baseline. We are seeing continuous trees rather than shattered fragments. This figure illustrates how our method works. Starting from the retinal image, the baseline pipeline produces fragmented vessel prediction. After applying TFFM with GET, the model captures global connectivity and reconnects the broken vessel segment. For our experiment, we used the fundus 𝐓𝐸 dataset. It's actually perfect for topology analysis because it labels arteries and veins separately, including crossings. This lets us really test if our model can handle complex branching. We used a standard augmentation pipeline, rotation, flips, intensity shifts, and Gaussian noise. Let us look at how we built the model. We ran a systematic comparison of architectures like UNet, TransUnit, and SwineUnit, where UNet++ with attention gate gave us the best baseline of 91% chi-score. Interestingly, we also used a efficient 𝐕0 encoder, and it outperformed the B4 and suggesting lighter encoders that preserve spatial detail better for topology tasks. TFFM was inserted at multiple decoder levels with adjusted grid size and neighbor counts to efficiently capture the global context. So, what is actually happening inside the TFFM? Inside TFFM, we convert feature maps into graph using cosine similarity to find similar neighbors. Then we apply graph attention to capture global vessel relationship and reconnect the broken segments. Finally, we learnable gate fuses this global information with local features while not losing the defined details and fixing the connectivity. On the loss side, we set the Chebyshev hyperparameter alpha to 0.65. This prioritizes the recall. We did this because a false negative breaks the topology. The soft cell dice cleans up the topology, ensuring the skeleton matches the ground truth. Here are the baseline numbers. You can see UNet++ with attention gate hitting a 91% chi-score, but even here we still saw fragmentation. High dice did not mean no fragments. That's why we needed to move beyond just picking up a good architecture. This slide shows the TFFM impact on the right. We took efficient B0 encoder baseline and plugged in the TFFM. The Betty error, which counts the total fragmentation, has dropped by 38% with other values. With our final setup, TFFM plus hybrid loss, we achieved these numbers, a combined dice of nearly 91%. And look at the predicted components, is 25.3 per image, showing minimal fragmentation. Here is a visual comparison. On the left, without the TFFM, you see broken branches, isolated segments. It looks like a shattered map. On the right, with TFFM, those gaps are filled, showing a reduction in fragmented components. We also wanted to check, did we just overfit the specific dataset? We have ran zero-shot inference on 5 other benchmarks: Drive, ChessTV, HRF, RETA, and STAIR. Now fine-tuning, the model held up very well. The cell die score stayed consistently high across all the dataset. These are the key findings from the TFFM block, and we can see it shows a 39.5% reduction in Betty error with our TFFM plus hybrid loss, and also with the efficient B0 encoder with a baseline. And of course, no solution is perfect. We found that while fixing the general fragmentation, we still struggle a bit at a complex bifurcation point, junctions. The recall is around 0.44 to 0.52. Also, highly pathological retinas, especially in the STAIR, increase the boundary error. Topology improves, but disease structure remains challenging. So we have shown that TFFM is an architecture integrated topology preservation module using graph attention for this task. It works well with hybrid loss to balance accuracy and connectivity. In the future work, we want to explore bifurcation error attention that might fix the junction recall issue, and we are looking at lightweight variants so this can run in real time. To wrap it up, we introduce a topology-aware framework that addresses vascular fragmentation by integrating TFFM with a hybrid loss function to capture global connectivity while maintaining local features. Our code is open source at the link on the screen. Thank you for your time. We'd love to hear your thoughts.